So this is the problem that we are trying to solve today with logistic regression. A bank is interested in building a credit rating model and the response value, which is the Y variable. Okay, so the response variable takes the value either high risk defaulter or low risk defaulter. So the logistic regression could be used to predict defaulters. And this is your Y variable. The Y variable can take the value either high risk, that is 1, or low risk, 0. This is the Y variable, outcome variable, or label. It can be referred as anything here. Any one of those terms will be used. So this outcome variable takes two levels. It can be high, right? It can be high or it can be low. Now, when you start building a model, it is always good to think about positive class. So remember, the positive class is the class level which the analyst is interested in. So in this problem, the bank is trying to build a credit rating model and they want to identify the defaulters. So the defaulters are high risk category customers. So the positive class or class of interest is the high risk category, or this one value here. So let's understand that clearly first before we build a logistic regression model or any predictive model. Identify the class of interest before building the model. So then we look at all the attributes that are given to us for analysis. We have age, okay, then number of loans. That means this person has availed these many number of loans. And you have annual income. So all the three variables I mentioned, these are continuous or quantitative predictors. Number of loans is again displayed. So you have some numerical or quantitative predictors here. And these two, marital status and mortgage, are categorical. So this is the second thing that we need to understand. The first thing is identify which the class of interest is. And the second is we need to look at the nature of the features or X variables that are used for classification of prediction. So now we know that two of them are categorical. So let's take this. This is the data set. Take a look at it. So you have high risk and low risk here as your outcome or Y variable. So you have high risk, low and high. Class of interest is 1. Then you have income, which is your continuous variable. Then you have age of the customer and loans. Now we have two categorical variables. So if you look at mortgage has two levels, yes or no. Right? So mortgage, it takes these values. So these values are referred as levels. And this is the categorical variable, which has two levels, yes and no. So that means levels is represented, let's say we look at it as K value. So K is equal to 2 for mortgage because it takes yes and no value. So whenever we have a categorical variable, you cannot directly add it to the model for classification. You need to dummy code it. I'm sure you remember this from your regression models, but let me just reiterate for completion's sake. So you need to dummy code these values. Dummy code means what we're doing here is how many variables are required to represent that single categorical variable. That is the main. So when we say we dummy code, because that's how the models are going to estimate the coefficient. So they cannot understand if everything is there in the same categorical variable. So you need to split these variables. So how many variables the k value is used? So for any variable, the number of variables required will always be k minus 1. So therefore, mod gauge takes k equal to 2. Number of variables required is k minus 1. That is 2 minus 1, 1 variable. So all we need to do is say mod gauge, create a variable called mod gauge yes. Then, so for these two people, let me put it. So, right? So when I say mod gauge yes, instead of the original mod gauge, what we are doing is this yes is true. So mod gauge yes for this person will be 1, and no for this person it would be 0, and this person again it is no, so it would be 0. So instead of using this variable, we are using a single variable because k minus 1, and we represent it like this. So this is very easy for a binary variable. All we have to do is change this yes to 1 and no to 0. So we probably do this with gender also, isn't it? So when it takes 2 levels, we just need a single variable to represent. Now, if you look at marital status takes 3 levels, right? So marital status, k equal to 3, because there are 3 levels it takes, other, single, and married. So therefore, number of variables needed to represent this variable is k minus 1, 2 vars. So in this case, let's take the same data. Let's assume that 3 levels are other, single, and married. So let's make this single and married to understand how to represent. So marital status needs 2 representations. So let's call this k minus 1, 2 variables. So I will say marital underscore single, marital underscore married. So I have 2 variables. So k was equal to 3, k minus 1, 2 variables, and these are here. So I need to check this is married. This is a married value. So this is 0, and married is set to 1. This is a single person. So this would be 1, and this would be 0. And this one is neither this nor this. So this is 0 and 0. So we need only 2 variables to represent all the 3 categories. Married, this flag is set to 1. Single, this is set to 1. And other category, 0 and 0. Usually the one that is not represented as a variable, that is this other category, is called the base, right? The one that is not represented as a variable, but when the other variables are set to 0, it represents the base, and in this case, it is up. So we need not do this manually. Of course, the software will do it for us, but it is necessary to understand that this procedure of dummy coding should be done before running the analysis. So we looked at 2 things. One is we identify the positive class or class of interest. The second thing is we looked at the type of variables, features, or X variables we used for the analysis, right? And we understood that the categorical variables have to be dummy coded. So that's it. So let's build the model now for prediction. So as always, we start with the business goal. We are building a predictive model to identify defaulters, that is high risk, and positive classes high risk. So that's what we are doing. So this part, we are reading in the file. We did this with all the data sets we had. So I'm looking at the type of data. So mortgage has been read as an object. So this is a string. Loans is fine, which is a number. Age is fine. Marital status categorical and read as an object, not a problem. Income 64 into 64 and risk, because it's a number, has been read as a number, right? But we know it's a class, right? So right now everything looks fine except for risk. Risk has been read as a number because we represented it using 0 and 1. So it's a so this part we just check if everything has been written appropriately. Yes. So because this is read in as a number, I make sure that it becomes the software understands that it is a categorical variable. Otherwise, we cannot perform a classification. So in this step, right, I am identifying risk as a categorical variable. So I create a variable called y and I add raw df.risk, right? So all this, the entire thing, right? This risk, I'm pushing it into a variable called y variable. So I'm pushing it into a variable called y variable and I make sure that it is a categorical variable. Then I look at the x variables or the predictor variables, predictors, x features. So I create a list here. Okay. And what do? I take in all the columns, okay, the column names, and I remove the risk. Why do I do that? Risk is the y variable for this problem. It's the outcome or y variable. And in this step, I am identifying only the x variables, the ones that are needed to predict. So that is why I remove the risk variable. So I'm just checking if everything has been selected. Yes, mortgage, loans, age, marital status, and income are inside this X features. This is just a list or name of the columns which contain X variables, right? So all the X variables are inside X features. So now I subset the original data frame. So this has only the column names. So now I need a data frame which has only the X variables. So I take only the X features. So if I say, so you can see, I have everything inside this except the Y column. I have a data frame with the X features alone. And what are we doing here? So the code, what I have done is made sure that Y is treated as a class variable or categorical variable. the next thing I did was select the X-varies or predictors. Third thing I do is split the data to training and test. You have already spoken about this. So we will build the model training data. Right? So that is what we do. We'll split the data into training and test, and we always build the model on the training data. So how do we split? So common ratios used for splitting is 60-40, 70-30, or 80-20. That means you reserve 60% of the data for training, or 70% of the data for training, and 80% of the data for training. This remaining 40, 30, and 20 are used for test data. That is testing the model, right? That is the unseen data. The model doesn't see this data. So in this case, I'm splitting the data into training and test. Okay. So I'm importing this library, which does this for me. So I'm splitting X and Y. You already know what X and Y are. We set up Y here, okay, the entire risk column, and we have X here, right? So I'm splitting that X and Y, and I say 30% reserve it for test data. That means I'm going to use 70% for building the model. Random state, if you use the same number as what I'm using, then the same number of same records will be used as the training data set when you use this piece of code. So it's basically for replication. So it is split the data. So inside X train, you will have all this 70%, and Y train will have the Y variable, relevant Y variable, and X test will have the test data 30%, and Y test will have the 30% of the test data's Y value. So let me execute this. Right, so that is done. So you have X train and Y train. So to see, you can do this. Right, so you have 172 rows. So originally we had 246. So you had originally 246 records. So this 70% of that, 172. So inside your X train, you have 172 records, 70% for train. This one. Right? So now we have the training data. So we need to do all the data pre-processing here before we build the model. So pre-processing should always be done after the split, not before the split. So what we're going to do is the dummy coding part. So we had these two columns which require dummy coding. So I add this into a variable called categorical columns. Sometimes you may have more than two, so it's easier to put them into this list. So these are the two categorical columns. And I say from this training data that we got, X-train, make sure that you dummy code. I'm asking Python to dummy code these variables for me. Okay, so pd.getDummies, you can look it up. You can look up and see what is inside that function. You can look at the parameters that are there. Right? So I'm telling the software to get me the dummies, and I'm saying drop first is equal to true. Okay. So when I say drop first is equal to true, I'm saying make sure that you set one of them as the base. So in this case, I had marital converted into two columns, and one of them is not added as a variable because that is the base, and that's represented using the 0, 0, which is what I'm saying here. If you don't say that, it will create 3 columns for marital. It will say single, married, and other. So if we know that this should be done, then what we typically do is we can delete that column and then work. But it's better to drop first, because right now we are relying a lot on the libraries because we are just beginning. So get dummies, drop first through means remove the base column. It need not be there for representation. I make sure that this column is integer. Otherwise, what happens is this function, Python function, sets it as a Boolean. So when it sets it as a Boolean, then there is a problem with the prediction. We need it as an integer. We are coding it as 0 and 1. We use that as a reference. So that's what is happening in this function. I get the dummy coded value. So let's see what is inside. So you can see that mortgage is retained as mortgage underscore by. So that is the dummy here. Mortgage, yes. It has made it into yes. And marital status other and single have been chosen. So we said drop married is used as the base. All right. So that means instead of other as the base category, married is base. So you will have marital underscore other here. This would have been 1 and this will be 0 and 0. So if you see what's inside, you can see this conversion dummy coding happening here. The second thing that we need to do is if the X variables, okay, so we split the data. The fourth step that we do here is pre-process and handle our predictors. We handle them first. What we did was we dummy code categorical variables. Second thing that we need to do is ensure that the X squares are not correlated. So if they are correlated, then they mean the same thing, which is what we are trying to say. So if X1 and X2 represent the same information about the customer in this case, then using both of them to classify Y is meaningless. Okay. So it is not correct to appropriate to use highly correlated variables. So we handle them in different ways. If both of them represent the same meaning, right? So we will be working with the data set later where we do this. So if both of them represent the same thing, then we delete one of them, or we use dimension reduction techniques like principal component to combine them into one and use them as X variables. So we need to make sure that X variables are not correlated. Now be very clear here. Here, when we dummy coded, we used categorical variables. When you run correlation, make sure that you're working with quantitative variables only. Don't push. Just because you have code for correlation, please do not add zip code, which is a number, say. Don't add it into the correlation matrix. Understand that it is a categorical variable, zip code. You cannot use it in a correlation matrix. So let's handle the second part. You have done the dummy coding. Then we look at correlation. So I use these libraries. You already must be familiar with them. So this is for, you can look them up. This is for plotting. Both of them are plotting. I just want to see a heat map. So I'm saying now all the dummy coded variables are in training encoded and test encoded. Both of them are there. This is the training data, right? So this was dummy coding in the training data, and the same dummy coding applied to the test data. Right? So now the model should be built on the training data, the encoded one, which is having the dummy variable. So here I run the correlation on the encoded data. So I'm representing it using a heat map. That's it. So you can see all the continuous variable and the dummy variables inside, because we said that it was int, isn't it? So don't worry too much about the dummy coded variables. Let's look at loans, age, and income, which are the quantitative variables here. So 0.41, there's a 0.64 here. Here, this is a dummy coded variable. So don't worry too much about them, the dummy coded. But among the numeric variables, if you find high correlation, then you need to worry. So right now, age and what's income? Yeah. So age and income seem to have some kind of moderate correlation, 0.41. Older, more income. Makes sense. But let's use it because it is not meeting, let's say if it's like 0.7 or something, 0.7, then we can think about it. But right now, we can use it. Just printing it if you wanted to see it. It's the same information. So we have done all this. So there's not much correlation. So we don't have to worry. So what we do next is build the Logit model. Training data. Right? Building the logistic model with the training data. So we split it, that we do first, and then we pre-process, and then we build. Now I'm specifically using the logistic regression model from the stats model library. One of the reasons is the advantage of a logistic regression model is getting that equation there. Okay, seeing how the input variables relate to the outcome variable. So, and this library helps us do that, see the coefficients. So that is the reason I'm using this particular library. So I'm building the logic model. I'm importing the stats model library, which has the logistic function. Now, we just split this code. So I'm calling this library, and this particular library requires you to manually add the intercept. So if you remember, the logit model is ln of the odds, which is y probability of y equal to 1 divided by probability of y equal to 0, right? And this is equal to so you have beta naught plus given into x1 and so on. Now this beta naught is the intercept. So that's what we are adding here. You need to add that constant before it starts estimating. That is a requirement for this library. So I'm adding that constant here. So let me say execute. And if you see here, it would have added this one, this constant one to all the rows in the training data. That's what it does. All right. So it is to be done if you're using this library, only then it can estimate your beta 1 and beta 2 and all that for you. So because we are using this library, I add this constant. If that is clear, I added the constant. Let me restart and okay. So I've done that. Now I'm saying build the logit model. So logit model with y variable, training data y, and this X train encoded with the constant. So build the logit model, and the logit is pushed into this particular variable. All right, so I'm setting up the equation, then I fit this equation. So when I say logic.fit, it is going to fit the equation for me. So you can take a look at this function. It right, so it will return the model instance, which is what we are getting here. Let me run this. So I'm printing the model summary. So optimization terminated successfully. So make sure that you see this message. Only when you see this message, you know that it has completed finding a solution for you. So it took 9 iterations to find a solution for you. So you can see that the model is logistic regression. It has used the logit function, and MLE is maximum likelihood estimator. So it has used that to determine the solution. Dependent variable is risk, and pseudo R square is 0.780. So you have all this output here, right? And a set of individual variables and their relationship here. So let's look at what this means. So let me just do this first. So yeah, this is the logic model. It has used the maximum likelihood estimator. Okay. So yeah, where's the chi-square? This value tells you that the model is significant, but we are not worried about this. It's a predictive model. So you see all this, it has used MLE and it has used Logit, and it has converged, which is very important. The model has converged. So what do we get out of this? This is what we get out of this. Right? So you have an equation. So the meaning here is ln of the odds ratio, that is your risk equal to 1 divided by risk equal to 0, okay, is equal to the constant value 19.64 plus the number of loans is minus, right? So minus 2.16 into loans. Okay. Age is minus 0.13. Then income is minus 0.004. Then 2.21 mortgages plus 6.1 the status other status single. So we have a equation here. That is the advantage of using this library. So you can see we have just used all this. This is beta naught and this is beta 1, beta 2, and 3 and so on. So now if you see all this, luckily all the coefficients are significant. So when we write the equation, we include all the variables that we included in the model. So we have written everything. All the variables are significant because values are less than 0.05, right? So we can find out that all the variables are significant, and this is the equation. When we build a predictive model, only significant variables are to be used for prediction. And luckily in this case, all the variables are significant. So we use all the X variables for prediction. Otherwise, we would have had to rebuild the model by removing the insignificant predictors, which we will do for the subsequent data sets. So right now we can use all these variables. And in this step, what I'm doing is I'm saying I'm adding a constant to the test data. I'm going to apply the model on the test data because the goal of the predictive model is to check how well the Logit model that we built with the training data works on the test data. So I add the constant and I say predict. This Logit model is where I have the model. So I say predict the probability values for me. The logistic regression model returns everything as a probability. So for the test data, it has returned probability for me. Okay. So this Y probability stores the prediction for each of this record. Now, how does it calculate this probability value? So let's look at that. So how did it calculate? Let's assume this was a test record. So when it did that random split into training and test, this particular record went into test record. Okay, so this is, but now the variables are something like this, isn't it? So mortgage underscore yes. This record would be 0 because it's a no. Loans would be 3. This would be, so we had marital other, then we had marital single, and income risk. And this is other category. So this is 1 and this is 0. So this is how this record would be seen by the logistic regression model. And you have an equation like this, isn't it? So we have an equation like this. So So what is the logit? So the model will calculate the logit for this particular record. So all you need to do is substitute in this equation. So you say 19.64 minus 2.61 into loans minus 0.13 into age minus 0.004 to that's 2.21 into kg equal to yes plus 6.11 status other plus 3.13 0. Right? So we have substituted this test records value into the equation, and this is the logit of this value. So the odds would be right. So this is the odds. Probability would be divided by so this is the probability value that is got here. So y probability for some record is this value. So what does it mean? So we already have spoken about this when we talked about the classifiers. We have a default cutoff of, when we did that confusion matrix, we have a default cutoff of 0.5, and anything greater than 0.5 is treated as class 1. So this is classified as risk. So that is the main. So you can see that the Logit model has predicted the probability values for all the records in the test data. I'm saving the actual value of y and the predicted value in this data frame because I need to build the confusion matrix to see how good the model is, right? So we have done that. So actually this is 1 and predicted probability is 0.99. So that's what I see here. We have a default cutoff of 0.5, right? So this is what I'm doing here. So I'm saying if the value is greater than 0.5, make it class 1. Otherwise, make it class 0. So if the y predicted df is predicted value, okay, this one. Create a column called predicted y. If you find the predicted probability value, this one, to be greater than 0.5, make it class 1, otherwise make it class 0. So what I have is actual y, I have probability values, predicted probability values, and this is the predicted y. If it is greater than 0.5, it becomes class 1. If it is less than 0.5, it becomes class 0. So you can generate the confusion matrix with the actual y and the predicted y value. This is the default confusion matrix from the sklearn library. This doesn't look very clear, so that's why I'm plotting it with the Seaborn library. So now it's easier to see. Actually 0 and predicted 0, which is the true negative class, isn't it? Actually 0, predicted 0, true negative. Actually positive, high risk, and predicted positive. This is this 33. And how many true records has it missed? 3 records. How many negative records it has missed? 2 records. So these two records are actually 0, but has been predicted 1. So they are falsely positive. So they are false positives. And this one actually 1, but predicted as 0. So false negatives. So we have this count, and you know how to calculate the 3 different metrics: accuracy, sensitivity, and specificity, isn't it? You know that ratio. So this is what is done here, right? Nothing complicated. I just get the sensitivity and accuracy. Because this calculation to get specificity is difficult, I'll have to write a function. I didn't do that. By default, there's something called classification report, which this library gives, which tells you, which gives you the model stats. So the accuracy of this model is 0.93. So the accuracy is 0.93. Now we know that there's an accuracy paradox. 93% looks very good, but we also look at sensitivity because we are interested in the positive class. So sensitivity, recall, is 0.92. You can see that here. This is for class 0, that is risk equal to low. And this is for class 1, risk equal to high, which is what we are interested in. That is the sensitivity. So recall, sensitivity for the positive class is 0.92. This one, we calculated it already. So 92% sensitivity and 95% specificity. So our model has percent accuracy, and we have 92% sensitivity and 95% specificity. So this is the goodness of the model. We are interested in the predictive part. We are using it to, so this is 93% accuracy, 92% sensitivity, and specificity is so much. So if the bank can work with this 92% sensitivity, if it is agreeable for credit rating, usually it's not, it would probably desire higher values. But right now, let's say it's running it as a initial model. So these numbers are good. We will say accept the model with threshold cutoff value, right? 0.5. So that is the conclusion that we will make. So please complete this. Of course, you would have a lot of doubts. So we will discuss that in class, but make sure that you complete the piece of code and come to class, all right?